Okay, ZK proofs, zero knowledge proofs. So we start with the overview of the ZK proofs and their details. Just what do they cover? What do they mean? What they are supposed to achieve for us? Similar to other cryptographic primitives that we start, we said what goal they want to achieve. We look some example at them, and then we talk about ZK snark. We talk about snarks in general. At this point, we don't go into detail of them, but just how do they show up and what type of ZK proofs they are. Then we talk about the application of ZK snarks. And here we get much more into how we make them. We haven't done this with any other primitives. This is the first primitive that we are going into detail of it. So you don't worry if you don't understand the mathematics. Even the mathematics, you don't need to understand to generate the ZK proofs. But the reason that we put it here is ZK sound a lot like magic to people. And the reality is the mathematics behind it is not complicated. So the mathematics you will see here at the section 5, they are basically high school mathematics. But so we thought that demystifying the mathematics behind the ZK proof makes them much more touchable object that you now, after you're going to implement some kind of a solution or deploy some kind of a solution, then you always have in mind you can also use ZK primitives. They are not some kind of mystify objects. So I thought that that will make the mathematics a bit more touchable. And we have a demo at the end to generate a ZK proof, but using tools that already exist. So even you don't need to know those mathematics to generate the proof, and this is more of a coding demo. Okay, let's see how much of this we can cover. I like the clicker. Oh, then I have to turn it on. Do I know how? Oh, on. I did it. So the problem with the ZK, so the problem that motivates us to do ZK proof, the biggest problem like is out there, is we have these databases out there, which we call them blockchain. And they're all in open because everybody needs to verify them. That is the golden rule of the blockchain. It shouldn't be in hand of one single central authority. So they need to be public. How can we do private operation on those databases in a way that nobody knows what they are, but everybody knows they have been done correctly? So that's one of the biggest motivation of ZK proof. So what is a ZK proof? So is a situation that the prover wants, somebody who has the information wants to verify to convince a verifier, which is the guardian of that database, for example, the validator, the person who need to believe in him, that that something is true without revealing anything else about that thing, except that that thing exists, is true, or is valid. When we talk about the ZK proofs, they are mostly interactive. I claim something as a prover, the verifier come to me and give me a challenge, then I reply to their challenge, and so on and so forth. But we turn them into non-interactive protocol because interactive is very non-automatized and not friendly with the, let's say, blockchain application or any application that doesn't necessarily have all the party around. So we turn them into non-interactive. We talk about how to turn them non-interactive later in that thing. Okay. So what can we show? There is it's basically any statement NP statements are a statement that they might be hard to find a solution for them, but they're very easy to verify. So we want the stuff that are easy to verify. Okay, so we talk about a statement that are easy to verify, but actually you can prove other stuff too. But so from the, again, API of programmers that are here, suppose there is a function that get a statement and it get a value for it. So you will see this a lot in ZK proof. People use like jargons that then make it very hard for other people to understand. But witness is basically a secret input. But they like to call it witness. But make the translation in your mind so you don't get lost. So you have a function. I give a statement and get a witness, which is the input. So you get the input and then return true or false. Like in this whole thing, I want to focus on some kind of a factorization. So the statement is n is equal to r times s. And then, so the statement is n, and I send the secret input r and s that I don't want anybody to know, and go into that function. If you multiply r by s and you get n, then the fact that r times s is a factorization of n is true. It returns true. So this is the relation. So the prover know a value like r and s that satisfy the statement, right? And they want to tell the other party that they know that that secret, that verify this statement, it returns true for this function, but they don't want to tell them anything about those secret inputs. Oh, question, Mike. Mike.
So, hi Tushar. So in this, the statement is in public, the witness is private or something that you don't want to show.
Yeah, in general, statements are public, so everybody knows the statement.
Witness is you hide.
They are secret information, yes. So they use the jargon public input and witness, and usually witness are the secret. So the statement is public. We know what we want to prove, but the witness is not. There are examples that the statement even is secret, but we don't touch them in this. Igor has Igor. Yeah.
Just I'm not clear on, is the witness another party or?
That's it. The witness is an input, is a value. For some reason, they call it a witness and confuse everybody.
I see.
They should have written here input, secret input. But if I tell you that, then you open the paper and this zero knowledge, you won't understand it.
Okay.
So they use that jargon, but it's basically witness is secret input.
Okay.
Okay. The developer part of it. So when you have a system that does the proof for you, it gives you this API. It gives you a proof function that you put the witness, the secret witness inside it, and you give the statement, and it should return a proof. And this is some string of bytes. You put the proof, you put back the statement in the verify function, you put the proof, it should return true, is the proof is valid if actually they had the witness. So the API look like that, and at the end, if we have time to do the demo, you will see I will run a proof, it'll generate a proof, it save it in a JSON file, then I give the proof to the verify function, and they return true or false if we tamper with the proof. Some example. So Schnorr signatures are ZK proof. So when I wrote this, I thought you have already seen the Schnorr proof, Schnorr signature, the mathematics of it, but you haven't. But Schnorr proofs look like this. Schnorr signatures are a pair of two numbers. And you want to prove this. This statement is true. S equals some blinding factor minus private key, another number E. So Schnorr proofs are a ZK proof because you want to prove that you know a private key that you put in this statement, and actually you also know R, you don't reveal R. You know a private key and R that you put in this statement, and this equality holds. So that's it. When you sign with a Schnorr, you prove that you know your private key without the fact the other party find out what is your private key. Question and the mic.
Isn't that true for any signature scheme? Because in a signature, you say that, like, you prove that you have the private key without revealing the private key.
But like maybe, but like our BLS is completely different. You multiply the private key with a message, and then you run a pairing. It's not clear. Like this is a protocol that we usually use completely in the ZK proof. Maybe philosophically is the same. But the operation here that I added blinding factor so you don't find out the private key is a specific in Schnorr. But yeah, maybe philosophically what you say is true. Risha.
Okay, so Schnorr signatures are based on ZK proof, and that's why we can't actually recover the public key, right? From
We
the
can't
signature.
recover the private key.
Yeah, the public. No, sorry.
The private key.
Yeah, private. Yeah.
Yeah.
Okay.
Because it's zero knowledge proof. I send you proof. This is a proof that I know the private key such that this hold. You can verify it by multiplying it with the public key, but you cannot recover the private key out of it. So this is a proof. You see, this is S and E are bytes of the proof. So the statement is the public key, and the witness, which is the private input, is the private key. Okay. This is the example I like more. So this one, we are going to use it all today. So we'll see it like 100 times. This is like RSA. So the prover knows a non-trivial factorization of n. So the prover wants to prove that they know n equal r times s without revealing anything about r or s. But they need to reveal some stuff. So one factorization is n equal n times 1. And because you don't know what is R and S, if they don't reveal anything, then they can trick you into that. So in addition to prove that R times S is N, they also need to prove that that R and S, none of them are trivial. None of them are 1. But that's basically all this there. They don't want to tell you anything else. R times S equal N, and they are not equal. So again, the statement is this factorization time equal N, and the secret inputs are R and S. So this will be our toy example for today. So ZK proofs need to have these properties. They should be, so we call one of the first property called completeness, is that if the claim is true, that I actually know the R or S, and if I know the private key, then the verify function should 100% return true. Deterministically should return true. That is called completeness. But they are statistically knowledge sound. And that means if the statement is false, with a high probability, the proof fails. That is all we can promise. Because, but the high probability, you can repeat it many times and you can make it as many high as possible. So you can ask them to generate more and more proof. And the probability if wrong will go to 0.00000. Very, very little. But the knowledge soundness is statistical. And they are zero knowledge. So they should reveal nothing else about the witnesses except that when you put it in this function, it's returned true. But they shouldn't be able to recover anything else about the witness. So there are many ZK proof before, but the modern way of implementing a general ZK proof is using a ZK snarks. So we'll go and see what are the ZK snarks. So ZK snark stands for zero knowledge succinct non-interactive argument of knowledge. So they are zero knowledge, or they could be made zero knowledge. So in a way that when you send the proof, it reveals nothing about the secret input that the statement didn't reveal. The statement says R and S are the factors, but more than that, it shouldn't reveal anything. There's a big thing here that this general ZK proof don't have is succinctness. They should, they are and they should be much, much smaller than the input and the statement. So the problem here is that the inputs will become very big and impractical in the current application. So you need some property that makes the proof much, much smaller than the witness. So maybe even the verifier does not have the power, even if you give them the secret, they don't have the power to verify the statement because the secrets are so big. So the proof need to be succinct. They are non-interactive, so that is another requirement. So you don't want to, ZK proof can be interactive, but when you use a snark, we want them to not non-interactive. And then they are argument of knowledge. Proof of knowledge means that the proof not only says the statement is true, but also says I know the secret that make the statement true. But these are argument of knowledge, and why they are not proof? Because they are computationally bounded. If the adversary has infinite power, infinite computational power, they can generate false argument. But the way that we stop the adversary from generating false proofs is by making it very, very computationally hard. Similar to public key, like if you have a lot of computation power, then you can find the private key. But we rely on the fact that the adversary doesn't have a lot of power, so they're computationally impossible to generate false proof. Okay. Yes, Mike.
I don't get it, the last one, because if the witness is an input, sounds that it's kind of reversible. So if you can compute a proof for a statement, you should be able to compute a witness for the statement.
The witness is the input. I didn't understand.
Is the input.
Yeah.
So if you can compute a proof for the statement and the witness, how would you be able to compute a witness on reverse?
You can't. So the ZK snark says nothing about how you found the witness. So for example, here, like the R times S factorization, the witness, the input are R and S. The snark doesn't help you to find R and S. It says, I don't know where you brought R and S. Probably you multiply them together and you got N. But I'm only going to, so that is the MP problem, right? The problem, finding those are very hard, but verifying it easy. So it says, I don't know where you brought the input. I put them in the snark, it generates a proof that says you have the input. But you don't know, but the proof doesn't say anything else about the input. It just says, this person who generated this proof knows these inputs, and that satisfies the statement, but I'm not going to tell you anything else. And it doesn't know how did they found the input. Okay. So basically, we can take any relationship that is easy to verify and maybe hard to compute, and show if we know that is true with the input that is secret, and we generate a very, very small proof. And that is the magic of the snark that make them practical for blockchain and current application. So even if the witness is the input is very, very large, the result of the proof. The proofs are very, very small. There's a question there, and we need a mic. Where is the mic? Risha, you have the mic. Maybe, yeah, sorry.
Cindy here. So could you kindly just explain to me the difference between now ZK Snack and Stack? ZK Stack. Yes.
I think that is even out of the scope of with all the mathematics and stuff. Starks, like Fry. I think Snark and a Stark. It could be, yeah. I don't exactly know. I know that Stark uses vector commitment. It could be. Is about the trusted setup? Okay, sure. So one of the differences is that the Stark does not use a trusted setup. Some Snark do, some Snark don't. So at least a Stark doesn't use trusted setup. So trusted setup is part of this process of making this a Snark succinct is to generate a private key. But that private key should not be known to anyone. So if after you generate that private key, you have to delete that private key before doing the verification. Before using the system, a Stark doesn't have that requirement. You don't need to worry about if they throw out the private key or they didn't. I will talk more about this trusted setup, but I have seen the Stark, but I don't know like what is this exact difference on the terminology. So there are many ways to make a Snarks. As I said, with trusted setup, without trusted setup, with different type of commitment and stuff. There's a lot of, because it has a lot of loose part from the time that you go from the problem to generate the proof, you can have a lot of choices. So there's different Snarks, but in this talk, I concentrate on Planck. It's one of the most popular Snarks, so you will see it, and actually one of the lecture in the afternoon is about Planck, so you have seen it in the morning. Okay. So let's look at some of the applications that the Snarks can have. So because of this succinct property, there is a lot of application of the Snark, which is not necessarily zero knowledge, but people use them because they are much smaller. Yeah, like, okay. Anyways, I'm going back to the Stark question. Like Fry doesn't give it as a small proof as a Snarks.
Yeah, some question here.
Okay, sorry,
Sure.
Borisha.
Yeah, one thing is just a long form of NP relation. That's it, NP.
Yeah, so NP relations are relations that are easy to verify.
Oh,
And
the
easy
P versus
means it
NP.
takes polynomial time to verify them.
Oh, the P versus NP.
But if there's a problem, verification problem is very take long time to verify, then we have very hard time to turn them in Snark. Because the Snark using polynomial, so.
Yeah, so the P relations cannot be used in ZK.
No, P relation are NP because they're easy to verify, but they are also easy to solve.
Okay, yeah.
But there are problems that are not easy to solve, or we don't know how to solve them easily, like discrete log, like finding the secret key from the public key.
But easy to verify.
But they're easy to verify. So they are also NP, and all the P problem are NP, but
Not
there are-
NP or P.
we don't know. But we know problems that are, we don't know if they are P or not. But yeah, we don't know the algorithm. So yeah,
Alright.
the common conception is that there are problems that are hard to solve, like the public key, like the whole cryptography is based on it. But they are easy to verify. So NP problem are problems that are easy to verify. If the problem is not very hard to verify, like like factorization is hard to compute, but it's very easy to verify. If the problem is easy to verify, then we can make it into a snark. So ZK proof, they help us to make a smaller proof that they are much faster to compute, to verify than the original problem, because even the witness might be big and just digesting the witness will take time. And they are proving something about a data set that is much bigger, but the verifier doesn't need to know the data set. So it makes the size of the proof it makes the verifier to have much less computational power. So these are application of ZK proof, which is not about, you are not supposed to know the big data set. If you want to, you can, but the verifier doesn't want to, because they don't have the ability to do it, because it's too much data. So they asking a prover to prove the data for them without the need for them to go and access the whole big data. So for example, you have a blockchain. It takes a gigabyte of data to show the state of it from the day one to there. But you have an app on the phone that wants to know one account is correct or not. And they don't want to read the whole blockchain to know that. So that's an application that somebody can generate a ZK proof for them to say what is the value in the account without the need for them to read the database. The other application is the verifier itself is a blockchain. So blockchains are very expensive. They're a smart contract when you write code on blockchain. You don't want to do like huge verification on them. So for example, layer 2 ZK rollups are like that. You have another thing that's another layer blockchain that had done something, and to the layer 1 they want to prove that they did it correctly. And if they want to submit the whole data to the base blockchain, that's very expensive. That is why they had their own independent blockchain. So they use ZK to prove that they did the stuff correctly. It's not that they want to hide anything, because their data is on the blockchain. It's just they don't want to submit a lot of data to the base blockchain because it becomes very expensive to submit big data. So these are the scaling application of ZK Snark. The other application is obviously privacy. So you have a private data, you want to use it based on some algorithm, and you don't want the people to know the data itself, but you want people to know that the algorithm you used it correctly. So for example, you have you have an account. You have some money. You want to pay to somebody else. It's a secret transaction. You don't want they know that you made the transaction. You don't want to know the destination. You don't want people to know the amount. But still, you want them to know that you followed the rule. The account wasn't empty. There was a positive money amount in it, and then you transfer the positive money to another account, and then you decrease the first amount from the first account. But all these values are secret, but the conditions are not secret. There's a question.
Yeah, my name is Gunjan. My question is on the first slide that where we are using zero knowledge proof in the rollups, L2 rollups.
Okay, I'm going back.
Even though we don't use the zero knowledge property, we use only snark property, then why don't we call it snark rollups?
I know. ZK is
very-
like so sexy. Everybody wants to use it. They are not even zero knowledge, right? Because it takes computational complexity to make them zero knowledge. If they don't want it, so they are not zero knowledge, they leak information.
Yeah.
But because they don't care, but they still call it ZK because
Okay, yeah.
people get excited and then they buy their token.
We have to go with that name then. And second thing, sorry.
Sorry, go ahead.
So in case where the balances are hidden,
in the second.
and all the operations are done using zero knowledge proofs. I'm just wondering, how do we show the balance of a user? Maybe this question is blockchain somehow, but generally on Substrate we can query the balance of a user. But how that balance is decrypted and shown without doing any operation? I mean,
So nobody knows the balance. Only the person who has the private key knows the balance.
okay.
So
Makes sense.
you are the only person who can tell other people what is there. And people don't really need to know the balance because you do the transfer and decrease the balance and give it to the other person, but nobody else, the other person sees that they got some balance because they have the private key to their account. But they also don't know what is your balance, right? So the way practically this be done is with a UTXO. So you spend the transaction and it results into an unspent amount. So there's no database like Bitcoin. No, there's no database that shows all the balance. You have to know the transaction to know the balance is about.
Oh, makes sense. Thank you. Just a funny part. That means in those cases, we have to keep secret and safe our mnemonics as well as the balance. If you forget the balance, then
No, you can use a mnemonic to decrypt the transaction, so you will see it yourself. Yeah.
okay, then we can see the
Yeah.
Okay, got it. Thank you.
Yeah. So in the ZK snarks Sanketev, so the proof is in a small size, but like I'm confused that in the examples you mentioned large amount of data that is blockchain, we can get it to like mobile app or light client or something. So that means that the data of the which is used to generate the proof, that means the statement, can be any amount of large, it doesn't matter while for verification.
I mean, the larger your data, generating the proof is harder. So your prover is generating the data, is a big computer, but still, at some point,
But then
you have a
why
limit on that big computer. But the
Then-
proof is all like, again, when they mentioned the Stark proof get bigger, your data get bigger. But for the snark, for many a snark, the proof size is constant, no matter how big is your data.
Yep.
But generating that takes energy from the prover. And we assume the prover had big computers, but at some point it become too hard to generate.
But still, like, it's feasible for blockchains, like some provers to generate like large amount of blockchain data, which is in hundreds of GBs to actually generate a proof?
There is method to do it. Like there is a recursive snarks.
Okay.
So Mina blockchain, I don't know if you know it,
Yeah.
but they generate a proof for one block, and
Yeah.
then they generate a second proof based on that block.
Ah,
So
okay.
the last proof that you get is actually proof of the whole blockchain.
Right.
But if you want a prover to start at day one to generate all the proofs
So
there,
block
then it
by
takes a
block you can-
long time.
Okay. And last, in the privacy, can you please?
I think Andrew wants to say something.
So I don't know if he said this, but a lot of times you're doing this off chain, the proof generation.
Yeah, off-chain is okay, but still, in general, I wanted to know,
But
like,
yeah,
is
but we will talk more about it in blockchains.
okay,
We're still crypto. We don't even know about a blockchain yet.
yeah.
Trying
But
to.
can you please re-explain the example of the privacy you gave, that the algorithm is private and that?
So I want to make a transaction, and I have some account that has some money in it. I want to give it to somebody else. I don't want to tell how much money is in the account. I don't want to say how much I'm paying, and I don't want to say who am I paying to. But I want to say I have the private key to this account. I can sign a signature on it. I'm sending some money from it, and when I send it, I decrease the account balance, honestly, and increase the target account with the same amount, and I transfer the positive amount and not a negative amount.
So it will be multiple ZK proofs or multiple witnesses, because there's multiple secrets, right? Your balances and all these are also
Yeah. You have multiple secrets.
Okay.
Yeah. I mean, my example also you have two secret R and S. No. Good. So that was the overview part, and now I want to go to show you some of what is happening underneath. You have a question? No. Oh, you have a question. There's a question here. The mic.
Thank you. It's Carla. In terms of, say, a decentralized identity, if you don't want certain information to be disclosed, age, maybe educational qualifications, I assume that data is what we're calling the witness. And who puts that in? So wouldn't someone be able to, on the blockchain, be able to find, or the originator of that witness, like how does that stay ZK, like without private?
So I don't know. You have to design your system. But suppose there is some authority that verify your education, no? So you can prove on the blockchain. So you go to the authority, to the education ministry, and you tell them to sign my education. And then you make this ZK proof that this statement, which is like you have a master, you have a bachelor, and sign with the key of Ministry of Education, resulted, you have a valid signature for this statement signed by this signature, and you put that proof on the database.
But it's obscured, so you couldn't see it on the blockchain. That
On the blockchain, there's only a proof
okay,
that can be verified, but it doesn't say what was the education.
okay, thank you.
Okay, so here we get to some of the elementary math of ZK snark. If you don't understand, it's not a big deal. A lot of people even don't know the math behind it, and still they are able to write ZK proof. But I thought it would help us to demystify, and then that way you become more familiar with the ZK proof. And you get a hint of how these ZK proofs are different from normal programming language and stuff like that. It's mostly high school math. There might be like 2 or 3 points that is more. But let's get into it. So yeah, so I wanted to be familiar with this. So that's it. Like you don't feel at the end you have to be able to make your own ZK proof or something. It's just you have seen this once, and then when people talk about ZK proof, then you don't just think is a magic. So the problem I'm going to focus on is the factorization problem, right? So that's what I want to prove. I want to prove that I have R and S that I multiply and I get N. And for the rest of the lecture, N is 21. So I want to tell you I have R and S that I don't want to tell you, that I multiply them together and I get 21, okay? The secret is R and S. So the big idea behind the snarks is to turn this abstract problem of I know two factor that is equal to N into some knowledge of some polynomial. So you know, like as I said, like there could be many different type of ZK proof, but if you want to generalize it, that you get the problem and you don't want to, you know, every time come with some creative answer. The algorithm to do that here is to turn that into a knowledge of a certain polynomial. So that is a polynomial if you haven't, you know, associated this -1 is wrong. I don't know why it's here. But basically is bunch of x to some different, the -1 is in the power, I'm sorry. But some number times x, another times to some smaller power, and a times x, and this is a constant. So these are stuff, I think, in middle school we were working on them and we multiply them together. But my goal is that whatever problem you give me, the education problem, like what is your certificate, the transfer of the money from the account, or the factorization problem, I need to have an algorithm to turn that problem into knowledge of certain polynomial. So instead of I'm telling you I have two factors that when I multiply them I get N, I come to you and I say, I know a secret polynomial. That if I know that, then I know the thing that I claimed. And then you can come and ask me question about this polynomial, and I'm not going to tell you what is the polynomial, but I answer your quiz question about that polynomial. And then if I answer the question correctly, then the verifier will be fairly confident that I actually know that polynomial. And because I turned my problem of the knowledge into the polynomial, then the fact that I know that polynomial means that I knew that knowledge. So that's the general idea of what we are going to do here. But how we are going to change this problem to a polynomial? So we have these conditions, which they like to call it constraint in the ZK-SNARK knowledge. And these conditions are some relationship between values, right? So private key times public key is a multiplication that times like some point give you the public key. That's some kind of a relationship between numbers. So a way of turning this, so there's a routine way of doing it. You turn it into arithmetic circuit, we are going to see it, but these are basically small polynomials, addition and multiplication. But I'm going to show you an example. So we turn it into this, and then we get all this small part, the multiplication and addition part that we have together, and we put them together, and we generate a big polynomial that encompass all this small part that we're running around, all these small conditions. And you make it one polynomial. There's many ways of turning these small conditions into one big polynomial, but the way that we are looking at it today is Planck, which is a simpler algorithm than the old one, which was QAP. But so that is the way I'm going. I will look at my condition, I make them into a small, simple polynomial, which I'm calling them arithmetic circuit, and batch them together. I make it one big polynomial, and then I try to prove you that I know this big polynomial. So let's go on the conditions that I want to tell you about this, I want to prove for you. So the first one is this, right? And it's a pretty simple condition. R times S equal N. There's only a multiplication there. So that's good because, so I can write equalities. That is all I can write. And here is R times S is equal N. And I have that condition. So the other one that I told you, right? That's if somebody come and give me factor 1, then because I don't see the factor, then I need to put some condition to prevent them from giving me a factor 1. Okay? I cannot put this. This is not a polynomial. This is an inequality. It's not an equality. I only can deal with equalities. I want to have an equality at the end and put the whole equality together to get a big equality. So this is not good enough for me. I can't put this condition R not equal to 1. So I have to come with a creative way of representing this with equality. Anybody can guess? But that is, you don't want to, you cannot say you are not satisfying a condition. You have to put a condition to be satisfied. This is the normal way to do that. We say, if you are honest and R minus 1 is not 0, then R minus 1 is invertible. So show me basically then I tell them to do some computation with inverse of R minus 1. And if they haven't lied, then they can do that computation. So then this is the condition I'm putting. I say, if put R minus 1 here and multiply it with some number that you know, which is not hard for them if actually they know R, they can invert it and then give that this polynomial should hold. It should be equal to 1, right? And if they were cheating and R was 0, then R was 1, then this becomes 0, and no matter what number they put here, they never get 1 here, and they fail to generate that big polynomial. Similarly for S, I have to put a condition for that. There is some non-trivial thing here that happens is overflow, and we deal with that when we code now. Always overflow happens, and then the code doesn't work as we need it. There's a question.
What are you asking him to show you? The value of 1 over r minus 1?
No, I add a condition. I say, don't tell me what is r because you don't want to tell me. But if you're honest, put r minus 1, whatever r you had, decrease 1 from it, and find the inverse of it in the field that they are working, wherever they are, and multiply it together, and then I can, and then prove for me that is equal 1.
Prove for you how?
We will see. But that's very similar to this, right? How I want to make them to prove that. But then I will turn this. If they have this equation, then they can generate that big polynomial. Then if they can show me that big polynomial, the only way they can generate that big polynomial is this equation holds. If they cannot generate this equation, they cannot generate the big polynomial. The other problem is overflow prevention. So, you know, like we think about r times n is equal to something, but we have a limit. And then when you overflow, then they can cheat and use the overflow to their advantage, that actually they use the big number, it overflowed. It didn't equal n, but it was equal n remainder of the overflow. So we are working remainder of some prime p. So anything that bigger than prime p, if overflow, then it become equal to, it might be equal to the n, but that is not what we want. We want an actual number that they are multiplied and no overflow in them. So this is the situation will happen. They choose a big R and S, and then they multiply them. They get an n prime, which is not n, but is n with some multiple of the overflow. And then all the equations satisfy because the mathematics is working in this overflow condition, mod p. All the mathematics is the remainder of p. And so all the equation that I showed you, all of them hold because they're computing there, and then they can show me the polynomial. So I have to prevent them from doing that. Again, so I should stop them from using R too big and S too big. If they choose R and S too big, then they can do this. If I put a limit on R and S, then I can stop them. So if I say R and S are smaller than the square root of this overflow factor that I have here, then I'm safe, because when you multiply them together, it won't overflow. But again, I can't do that. This is an inequality. The only thing I can ask him to show me is equality, so I can turn them into polynomial. So then I have to find another creative way of forcing this. So again, the standard way of doing it is basically doing binary decomposition. That's Andrew was talking about. So I forced them, I asked them to write R in binaries, and then I cut it at some point, and I say, I don't care if your R is bigger than that many bits, then I reconstruct it again. If it's too big, you can reconstruct it, you don't get back R. So in our example, which my factor is 21, I don't want to let them to have any factor bigger than 8, 7, bigger than 7. So 8 is not accepted. So to force that, I say your number only can be 3 bits. And to force that, then I say, decompose your number into this, and then give me 3 values that I can multiply. The first one, take the first one, add the second one times 2, add the third one times 4, and I will get the R. That should be equal R. This is equality, so I can enforce this. There's still some caveat here. Because they don't tell me what is R0, R1, and R2, they can cheat and not put 0 and 1 in it. They can put another value which is bigger, that still work, that I don't see what is the values here. So to prevent them to cheat about that, also I need to prevent them from using anything besides 0 or 1 instead of all this thing. And the standard way of doing it is I ask them that they should satisfy this equation. So now I have this equation and this equation added to all the list of equation relationship that I want them to satisfy. There's a question? No. No, there is. Oh, there is. Sorry.
So in this, like if we say that the R is 3 bits, as you said, right?
R is bit, yeah.
No, bits and 3 bits also, like R0 plus
Oh,
2.
yeah, R is 3 bits. Yeah,
Yeah.
R0 is bits.
So
Sorry.
if it is small in size, if R and S are small in size, like isn't there a problem that people can, like write up loops or something like?
Yeah. Of course, you can factorize 21, right?
Yeah.
But it's just a toy example.
Okay.
So then if there is more, then you have much more bits here, right?
Okay.
In a real life, if you actually
real
want to do it, become very big. But the problem here is that I only, in every relationship, I can handle, I said arithmetic circuit, I only can handle one addition. So
Yes.
it would become a law of addition, then I didn't have enough space in the board.
So then what we do in real,
No, in real thing, you don't have this, you can use as many, you can use a law of like, in real world, there are millions of condition when you write this stuff.
and how much like snarks and ZK proofs like on blockchain we use?
I think few millions relationship is normal, and like Zcash relationship is probably few millions relationship.
Okay, and there's no fixed way to tell like how what's a big number. Like it can be anything depending on different
I
platforms.
think nowadays if you hit like past 2 to the power of 25, 26, then become impossible.
Okay, thank you.
Yeah.
Sorry. So my name is Gunjan. Using some, for example, we say we are trying to restrict the numbers up to 3 bits, but
Yeah.
using 3 bits, maximum number can be represented. Let's say our P is 5.
Yeah,
But,
yeah.
But this can.
Yeah.
check
But my
more
P
than
is
5, so-
yeah. But my P is bigger.
Yeah.
I will choose the P. So I have a P, but no matter how big P I choose, you still can cheat because you can pass it.
No, so it's like this can check if the number is smaller than or up to up
Than
to 7 or
7.
not.
It just check is less than 8, independent of the P.
Yeah, less than 8. But if P is 5,
Is P5, then you shouldn't allow 4, right? You only should, you say, I only allow R0 and R1.
okay.
Because, but P is not, P is chosen by the verifier almost, right? I can tell you in which field I want you to prove this. So I can make the P bigger. And I could have made this bigger, but it would result in much more condition because for each of these bits, I have to add one equation. And then I wanted to list you all the equation in next slide, and then it become too many equations. That is why I stopped it here.
Okay, thank you.
But there is no real restriction here because but there should be some restriction. But there's nothing say, oh, 8 is a big number. I could have gone to 1 million, which is 2 to the power of 20. So I could say, or it can be, or like a RSA, which Andrew said 512 bytes. I could have gone very, very big, but still I have to put a limit. And the problem with this was that every limit I put is add one equation and then become too many equations. So I stopped at 4. At 3 bits, yeah.
Thank you.
There's a question there.
Not a question, it's just a request that probably you can, for everybody else, you can show through 21 all these things. It would be easier for
one, what?
For your 21, that is it 7 into 3 or whatnot, right? So, and did
Yeah,
you pick 21?
but the reality is that I'm a verifier. I don't know anything. I'm just
No, I mean,
designing this system for
if
the
these
prover.
equations you can walk through with 21 as an example, and did you pick 21 from blackjack?
No, I don't know why they choose. I wanted this not to be bigger than 7. So my biggest factor would have been 7. But let's look at it, okay? So the reason that I'm not talking about what is R and what is S, which are 3 and 7, right? Is that the verifier don't know them. So I want to pretend I don't know them. So I want to write them in a small, easy representable equation, and these are called arithmetic circuit, I guess. So I only can have one multiplication and one addition. So this one is R and S comes in, and then you get N. So this is the relation, and they like to call it gate. Another jargon that you will see here, but it's basically a simple relation that has 2 input and 1 output. So this is the condition for multiplication, factorization. This is the gate for, whatever. It's a relationship for, I add -1 to R, and then multiply with this new number. This is a new secret input to the system, you see? because I don't know. My division doesn't happen in this arithmetic circuit. You only can have addition and multiplication. So they have to compute it on their computer and then add it, enter it to the system. And then when they multiply, you have to get 1, right? And this one, which was you add R0 plus 2R1, and then you add them to 4R2 because each of this addition only can get 2 input. So I have to use 2 of them, and then at the result, I want it to become R. Oh. Okay. So here I wanted to, so that was that was this, and I wanted to talk about CIRCOM now. So CIRCOM is a programming language, and it helps you to write stuff like this that I showed you. And as you see, the programming language here is different than Rust. You can't have if, oh, there's a question, sorry, go ahead. Yeah, you, Risha, sorry.
So yeah, in the circuits and in the from overflow prevention and in the circuit, right? So I was asking, the Plonk actually because we are the demo is on one problem, right? For finding the factors, okay, proving that you know the factors of 21, right?
Yes.
Yeah. So because most of ZK snacks circuits are general purpose, right?
The circuit is not general purpose. Plonk is general purpose, right?
Okay, yeah, so like a problem can be general purpose, but then Plonk transform each specific problem to map one circuit for each, right?
It transforms it to one polynomial, much more than that. There's also a plumbing polynomial. So it transfers it to few polynomials.
Okay.
But Plonk is like a recipe from the cookbook, right? It says, if you have this problem, apply this recipe to this algorithm to it, and then
it will transform it
to those polynomial, and then from those polynomial, you can easily generate proof.
Oh, okay. So kind of Plonk is kind of like the starting point for each of the problem, and then.
But you have to write your circuit yourself. There are translators from Rust to the circuit, but you end up with being a less efficient circuits rather than you write your circuit yourself.
Okay.
There's a question.
Yeah. So can you point out like which part of like so far we have done through safeguarding thing. So is the Plonk the algorithm which can be multiple ways? Plonk is just one of them, I guess. So is the part of that action is an action, or which part of this
It's
process
after
is
this? After this is Plonk.
after this?
So this part is writing circuits.
This is common for every.
Every
ZK proof.
snark at least. You have to write your circuit first. And then after that, we apply Plonk to it. So I'm going to just show you the circuit, how does it look like in the CIRCOM, okay? Maybe I can use this guy now. Somehow successfully or unsuccessfully. Okay, I'm coming here. And let me go on 5. It's called circuit.circuit. Okay. Where am I? Here. So I don't know how big I should make it so you guys see it. It's good? I can take the whole page, I guess. Or maybe I shouldn't, because then I can look at the circuits, no? So I'll just go a bit over the code, just maybe more easy part of it. I don't go over the more complicated, but these are basically what I told you. So maybe I will put the picture I had here. So the first one is not equal 1. So these are like functions, right? So they're a function, but we call them template here because everybody needs it here. And they should represent exactly this equation there. So I'm going to the non-equal one, this one, right? So I said I'm getting an input, one input, which is R, and I get one output. that it should be 1. And it doesn't have an output, actually. I think I can remove the output. But so what I have, I will compute the inverse, but the computation of inverse is not in the circuit, right? That is why there's no equality there. But I don't want to bore you with the detail. But I compute the inverse there and just say the input minus 1 times the inverse should give me 1. And this is how I say this circuit should enforce that. Go ahead.
Yeah, suppose in this template, I have to return only inverse. I'm not going to check the next line, the equality to 1. Is that valid to get the inverse via that template?
You can, I think you say out is equal to inf.
So I don't do the next line. The last line I don't do. And
Yeah, but then it won't add a criteria to your circuit. So if the inverse actually a lie and it doesn't actually invert, it passes. That you have to verify it because there is no way to invert into the circuit. In this case, you only had multiplication and addition. These are the only thing can be enforced. So if you write inverse, it's not going to enforce it. And the way in the language of CIRCOM to enforce is to put 2 equalities. And if I put 2 equalities there, it doesn't compile. It says, I don't know how to do enforced inverse. So you have to enforce it yourself because inverse doesn't exist in the language of CIRCOM. So that is that. This is, I'm not going to go through it, but this is, you see, I decompose the bits here. And then I add them back together here, and I enforce that the sum of the bits are equal to the input from the beginning. It limits the sum. So I'm not going more in detail into this. I just go to the last function. Am I there? I just come to this more exciting function, and then I come back to you. I don't know how to keep it the whole thing on the page. But I guess it's not a very big deal. Okay, somebody has a question. You have a question?
Yes.
No, somebody. Oh, who?
Yeah.
Oh, I see. Okay, sure.
In the bits one, why do we do the bits I multiplied by 1 minus bits equals 0?
Because I don't want them to lie and put a non-zero or 1 value in them. Because I want, if they put bigger values, then they can have it like a non-binary decomposition, but still when you add them multiply by 2, it becomes equal to the number. So I want when they decompose, the bits are actually 0 or 1 and nothing else. So this satisfies only if bits are 0 or 1. If you put another value, that will fail and then it won't make a proof. This one is on the PBA content repo. Yeah, material factorization example, ZK factorization example. But let's look at the last function. So it says, I make some copy of this circuit that helps me to verify R is not 1. I make a copy of the, and I make R is not 1 is equal not equal 1 copy, and I give R to it, and I say you have to satisfy with this double equality. And do the same thing, and then I say I make a circuit with num-bit with 3 bit only, and I call it R is integer less than 8. And then with this 2 equality sign, I say this has to satisfy this property. If I give R as an input, this has to satisfy. And then I do the same thing for S. And then that criteria, which is the easiest one, you see, I put a criteria that says R times S should be equal 20. So then I have the circuit. It doesn't mention anything about R or S, but it's put some criteria in them. And then that's how you write the circuit in CIRCOM. So the closest you get to this, probably you want to write some circuits in CIRCOM. And then let the Plonk compiler make the rest of the work. But I want to tell you what the Plonk compiler is doing so you know the magic behind it. Okay. And then I have this, and then this, right? That was good. It's a bit hard. Okay. So we talked about this. So from here on, okay, Risha is here.
Yeah, Mauricio. So my question concerns on if we allow bigger number on R and S. You said like they can cheat and when multiplied they can yield to the answer. But then how, if they are bigger, how can they cheat?
Okay. So I do example, okay? It's all Risha's fault. But look at this, what happened. I said everything we do is modulo some p. Okay? So now I'm going to show you in the computation. I have to go to here and do this. Stage. Okay, so I don't know anything about R, right? And I don't know anything about S, and I'm a prover. I'm going to put that in the circuit without the condition to make them smaller than 8. And I'm going, the P that I'm using here, the verifier says and comp P equal 89. Okay, this is a prime number. Right? So I say do everything overflow over 89. And then you come and tell me, prove me that you have 2 factor. And the 2 factor I have are 2 and 55, which result in 110, but you don't know, right? But you had put the condition that 2 times 55 is equal to 21, but everything is remainder by 89. So then I can cheat and show 2 and 55 and tell you that's their factor. So I have to limit them so they are not big. So you cannot cheat. Okay, so the Planck strategy is good if you listen, because then the afternoon talk is also about Planck. And then you have a context about it. Okay. So as I said, oh, there's half of the thing is taken, sorry. So as I said, we want to turn all this small relationship, which we call them circuit, the set of this small relationship into one big polynomial, and we call it a trace polynomial because it actually shows the trace of what our friend was saying. You put this value 3 and 7 into it, and then you run it. You see all the variable, what the value gets. It looks like that is trace polynomial. So that is why we call it a trace polynomial. And then this trace polynomial should have so I give number to this circuit that with a small sub-circuit that I gave you, circuit 1, circuit 2, circuit 3, circuit 4, all the relationship that I have, I give them a number, and this trace polynomial at this number should give 0. That is the way I'm going to say that is a good polynomial. If this polynomial is 0 at 1, 2, 3, 4, because that represent at condition 1, condition 2, condition 3 satisfy, then you actually satisfied all the condition and you have the secret. And the verifier should be able to test that you have a polynomial that gives 0 at all these conditions. And if that works, then they believe that you are right. And if it doesn't work, then it's not right. The problem is here that they should not know this polynomial. Still, they should know that this polynomial gives 0 at all this place. But this is another problem. The first problem is to generate a polynomial that gives 0 at 1, 2, 3, and associate 1, 2, 3 to each of these conditions that I did. Okay, so here become maybe one of the scary part of this, but I saw it in the talk in the afternoon, so you will see it again. But it's nothing scary about it. So Planck has this equation that you can represent either multiplication or addition into it. And I call it a universal gate because you can also, all of the picture that I showed you can be represented with this one equation, which is a bit scary, but there's nothing impressive about it. It's just have one addition into it and one multiplication into it. So suppose the left input is called A and right input is equal B. I'm using this notation because every time you see this gate, it looks like they use the same notation. So I want you to see it from here. I could have used a better notation, but that is less scary. But because you are going to see it over and over, if you look at the literature, I use the same thing. So this is the relationship. This is this is some general relationship that every of these small circuit, you should be able to show it because it says some constant times the left input, some constant times the right input, some constants times the output, which is n here, for example, some constant times a times b. So here the input are multiplied, plus some constant, the n equals 0. The good thing about it, you have so many flexibility, you can represent each of them here. So in this, there is no addition of the right and left. So these two are 0. And yeah, I lied. The output, there is no output. This is a constant. This 21 is a constant. So this is also 0. And there is 1 here because you just multiply a times b. So qm is 1. And qc is the constant that's n, which is minus 21, right? Because r times s minus 21 should be 0. So this is a scary equation, but the whole thing is that I can represent multiplication with it and I can represent addition with it. And it's nice and I can repeat it all the time. And the fact computers like to repeat and iterate over the same thing, it helps my proof become simpler. So these are the constant QL, QR, QO, QC, and then A, B, C are the input and output. So all the operation that I told you can be written as a form of this. So for example, I described this, right? So QL is 0 because there is no addition. QR is 0 for the right. The output is 0. And the multiplication is 1 because it's R times S equals the constant is N, which is 21. And the right input is R and left input is S. When I'm going to run it, this becomes 3 and this becomes 7. But for now, I'm just putting this. And the output is 0. Okay? And I gave number 1 to this gate. So I'm going to number them. I say, this is number 1, this is the condition. And the condition is written in the Planck gate. I'll go over this and then maybe we get a break and then we come back. Okay? This one is all the condition on R. So the first one, it says add the first 2 bits and put it in that value, and then the second one it says add that value to 4 times the third bit, and you have to get R. The problem is that this equation, the universal Planck gate, only has 1 plus, right? I can't add 3 things here. It has only 2 inputs. So I had to use 2 gates to represent this addition of the bits. The third one, which says the bits should be either 0 and 1, so Ri is either 0 or 1. It translates to this, so it's like Ri times Ri minus Ri, the third one, which is number 4 because I already used 1, right? So this one, it says minus Ri, and then this is for the multiplication gate, which is say Ri times Ri. Both of the input are 0. And then I repeat it for R1 because I want R1 to be a bit, and I want R2 to be a bit. So these are repetition of the same thing, but for different Rs. And then the last one is the equation for enforcing the inverse. So I gave them number. So that one, the multiplication gate was number 1 and 2 and 3 and 4 and 5 and 6 and 7. So I repeat that for S, right? That is exactly the same table. This was for R, and you have exactly the same thing for S, the same condition, so you have all this table for that.
Excuse me.
Yes. Oh, okay, sure.
On the previous slide. So it seems Q1, QR, Q, all Q are irrelevant because why do we have them? Like if A is there with its value, then it will be there with its value.
Why do we have it? Sometimes we multiply them with some number, no? Maybe we multiply by 2 or 3. Like here, like you multiply the left value by 2. So I have to have some constant here. You see? The left value is 2, and here the left value multiplied by 4. These are constant, not the input, but always I multiply by 2 and always multiply by 4.
Okay.
I could have put them inside them, but then I have to change the definition of R and S. You know? So for now we made these tables. that all our equations are there. I think I take a pause here and then we start in 15 minutes. Here we are. We built our table of relation 1, relation 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So basically, if the prover has R and S that can satisfy this 13 relationship, then they are not lying and they have a factor for n. And the next step that we take, we have to take this table and turn it into the polynomial. And this, again, in the ZK jargon, is called arithmetization, but it's just a scary word to do something simple. Okay. Yeah. So that is basically the math that you might have not seen in high school till now that we used. And it's not even a complicated math, they don't teach it in high school usually. It says you can always, you have a vector, so a lot of you have coded, right? You have a vector, you can take that vector and make a polynomial out of it. You can always do that. That is a mathematical fact. So what do I mean by that? I have this table, right? So this is a vector, QL, right? Is a vector, 1, 1, minus 1, minus 1, minus 1, 0, and there's a 0 behind because I didn't write gate 1. This is gate 2. So there is 0, 1, 1, minus 1, so it's a vector like all the vectors you do in the programming. And then you can take that vector and find the polynomial that when you put 1 in that polynomial, it gives you the first element of the vector. When you put 2 in that polynomial, it gives the second element of the vector. Put 3 in the polynomial, it gives you the third element of the vector. So instead of running with the vector around, you can actually take that polynomial, and these two are basically equivalent. So instead of storing the vector, you can also store the polynomial. So that's called the Lagrange interpolation. It takes a vector and gives you a polynomial that's at a specific place, like 1, 2, 3, 4, 5, 6, 7, gives you the value of the vector. And so I can do this Lagrange. I can do this for all these vectors I have. How many vectors I have? 1, 2, 3, 4, 5, 6, 7, 8 vector. So I send them into this machine, which is called Lagrange interpolation. Each of them give me a polynomial outside, which at 1 is equal to the first element, at 2 is equal to the second element, and so on. The other polynomial at 2 is equal to, at 3 is equal to 4, at 4 is equal to 0, at 5 equals 0. So I will end up with 8 polynomials. Oh, 9, okay, sorry. Because the other table has gate number 1 and I don't have it, sorry. So the question is why I start gate, no, we started gate number 1. It's just that table that has gate 1 is not attached to this table, and I was lazy to make a new table, sorry. So the index 1 is here, and then 2, 3, 4, 7 is here, and then 8, 9, 12. But you should imagine that this is a big, big table. I start from 1 to 13, right? And then I get one polynomial for each vector. That at each number, it gives me the value of that vector. Because this gate thing, Planck gate, was valid at each these values, then if when I get polynomial for QL, I get polynomial for QR, I can just replace it there. And then this polynomial equation will be valid for all this gate 1. If you put 1 in this, it gives you the first gate, the first relationship. If you put 2 in it, it gives you the second relationship. So this equality hold with all these polynomials, I don't know, 9? Why 9? 1, 2, 3, 4, 5, 6, 7, 8. No, I don't have a polynomial for this for now, actually. Later I will show the polynomial. So all these 8 polynomial multiplied together, it gives you a big relation, big polynomial relation that at 1, at 2, at 3, at 4, till 13, it holds. Risha, okay.
Yeah, Mauricio. So in the table there for gates, so as for example, the gate the Q1 and QR and QO and QM. So one thing is we are using the Lagrange interpolation, but then we don't have the mapping. Okay, we don't have the. Okay, if you take like say Q1 and if you input a value, it yields 0 as the first row of the table,
Yes.
and the second the same. But then we don't have the
R.
no the okay the we don't know the equation of Q1 for us to get the value 0 at first.
It does. That is the magic of interpolation.
No.
It gives me a polynomial.
Yes, but
And
then
that polynomial I show you to you, if you put 0, it gives you the value as 0.
yes, but then the Lagrange takes x and y of values and then interpolate it to give a polynomial, right? But
Yeah.
I'm asking,
What is x and y?
yes.
X are here. X are gate numbers.
Oh.
X are these, and these are the y values. So I
Ah.
put 2, it should give me 2. I put 3, it should give me 2.
Oh,
This
okay.
is x.
Oh, okay.
Is artificially made because 1, 2, 3 are nice number. I could have put orange apple, whatever I could put it.
Okay.
But I put 1, 2, 3 because they're nice numbers. And in real SNARK, we don't put 1, 2, 3. We put root of unity because it's faster. But now these are nicer number to explain, so I'm putting those. Okay? So I found the polynomial. The x is always the gate number. Thank you, Farisha. And I found polynomial for QL. I find polynomial for AX. I found polynomial for QR. And then I put them in the gates of the Planck relationship. And now this relationship should hold because x 1, 2, 3 till 13, this relationship should hold. And it give me a big polynomial that should hold there. And this is basically the polynomial that the prover need to prove that they have it. Because this polynomial that is 0 at 1 to 13, because the enforcer relationship says this polynomial should be 0 at 1 to 13, if the prover proved that they have a polynomial such that is 0 from 1 to 13, then they are not lying and they have the factors. Go ahead.
In this, the gate number is how the gate numbers are assigned. Are these like 1, 2, 3? You assign them from start, or is there a maths of that also?
I use arbitrary 1, 2, 3, 4, 5, 6 because they're easy to deal with. In real life, they use other numbers that make their computation faster, make the Lagrange interpolation faster, make the...
Or they are assigned in form of the orders, like you first do the factorization circuit and then you do the prevention factor gate, and are these?
No, these, so I need the factorization to put this stuff here, right?
Yeah.
If I don't have, I cannot make Lagrange interpolation. Lagrange interpolation doesn't work on R that is unknown. These should be known. So the prover knows them, put the value here, and then get the polynomial out of it. For these, they are always the same number in ZK proof. They are root of unity. For some reason, they
But
make
these
the polynomial
these
much
numbers
faster.
are associated or marked related to the gates that circuits that we discussed earlier. Is it like that?
No, it just goes from the first root of unity to some power of root of unity. It's just if as much as I have 13 gate here, if you had more, you had 20, then you will have 20 of them, but they're always the same number.
Okay.
There's a root of unity 1, 2, 3 basically, but they're not 1, 2, 3. There are some other element of finite field that
Based on how your polynomial equation was created, the gate numbers can vary, right?
is based on the P that you chose. That prime that
Okay.
you chose,
Yeah,
they're
yeah.
different. But then after that, they are set. For all the proof that you're
Then
using
they are
for
set
that,
for
they are
it.
the same numbers. So I'm just going to show you the demo of making this polynomial. So you see this is a touchable object and it's not some magic talk. Okay. How should we do? Okay, I can turn this guy on again. So we are here. And let me go here. Interpolation, let's say. And then I'm here, no, okay. Interpolation stage. Okay, it's good now. You can see it. So I just put this here. The circum, the P that circum uses is this. is a very big piece, so you can do a lot of proof in it, but still is a finite number. But I'm going to use this P because that is enough for me, okay? So this one is going to overflow. So all my number are mod RP, which is this. Here is basically that was the first column of the table. So you don't see the gate 0 again, which is 0, but then you see the second number is 1, 1, minus 1, minus 1, minus 1, 0, and then this one was repeating for the S also. So I put this column into that vector, this column in that vector, all of them in that. From now on, because I will need to do the Lagrange interpolation, I have to tell what is R and S, so I can compute all these middle values. So I can compute the polynomial. If I don't know the secret, I cannot compute the polynomial. So I give them the secret here. And then I compute R0, R1, and R2. This is binary decomposition, right? And I have this value R01, which is addition of R0 and R1. So I put it there. And then I make this input vector, left input vector, which is A, which is start with R. You don't see it again here, but then it's R0 and all the other stuff. And then I make a vector for B with all this stuff that I compute. And I have a vector for C. So I make vectors here, right? All of them are vectors. And here the answer of what Risha said, I use x value 1 to 13, right? And then I tell them to generate me a polynomial that is actually equal to that QL values. And make me another polynomial that's equal to QR values. And another polynomial that QO value, all this polynomial together. And after I'm doing that, I'm going to get the trace polynomial here, right? This is the Planck equation that you see here in the bottom. I'll generate it there. And then it will be generated. We will see it later. I'm going to run the code at the end. But so basically here at this point, when the code arrives here, you find this big polynomial. I will run it. You will see the polynomial. Okay, let's get back to our slide now.
Can you run this code?
I will. I just talk about zero test and then I run the code. So we did this. Now, the proof was that I have a polynomial that is 0 at 1, at 0 at 2, at 0 at 13. That shows that it is the relation 1 is satisfied, relation 2 till relation 13 is satisfied. So what the prover needs to show that it has a polynomial that is 0 at 1 to 13. That is called zero test. There's another thing that I skipped, and that is actually the complicated part of the Planck, is the wiring test. So what I haven't been testing here is that I said this should be equal R01, and here I said R01 plus R2 should be equal R, but I didn't put any constraint on myself as a prover that this one is exactly equal that. I didn't cheat. I put some values here and another value here, and I did the interpolation, and it's satisfied. I have to put a constraint, a condition that the wiring or the plumbing from here to here was right, and I actually use this value here. So that will result in another polynomial called the permutation test, which gives you another polynomial, which need to be 0. But that's much more complicated to explain. But essentially, is another polynomial. This is a trace polynomial, should be 0 from 1 to 13. And the permutation polynomial also should be 0 to 113, but I'm not going into the detail of how to constructing the wiring polynomial. And we just stay with the zero test here. So how are we going to do a zero test? So the prover says, I have a polynomial which is 0 at 1 till 13, means that the relationship holds. So that means this polynomial should be able to be written as a factors of polynomial x minus 1 till x minus 13. So if a polynomial has 0 at 1, then it should be divisible by x minus 1. If it has a 0 at 13, then it should be divisible by x minus 13. So if the prover actually made a polynomial that is 0 at 1 to 13, then they should be able to divide fx by this polynomial and get a qx as another polynomial. So that is how we are going to use it to verify that they actually had a polynomial that was 0 in 1 to 13. So I'm going to verify this in Sage. So I show you that the polynomial I made is divisible by this polynomial, which represent all zeros from 1 to 13. And then we continue with this. And this thing that I show you doesn't work for ZK because I need the polynomial to do it. We are back to Sage, so. And this other mic is open, so I can work. What happened? I closed the buffer. No, it's here. Okay, it's here. I go to Sage here, okay? So I'm going to run this code, and I hope if it has an error, then I will fix it, okay? 1, 2, 3. Okay. So I ran it. At the end, I just show you what was printing. So first it prints a trace polynomial, right? This is the trace polynomial. You see it's the polynomial of degree 36. It became very big. That is how it works. Like the prover has to deal with polynomial of degree million degrees. And they have to do an operation on them and prove that they have 0 at every polynomial. Then I made the 0 test polynomial, which is x minus 1 times x minus 2 times x minus 3 times x minus 4, right? This is x minus x value, which x value was from 1 to 13. So then I made the 0 test polynomial. I'll multiply them together. I got the 0 test polynomial here. And you see this is degree 13 polynomial, right? I multiply 13 as one degree polynomial. I get a degree 13 polynomial. The claim is if the prover is not a liar and the R and S are actual solution to the system, this polynomial is divisible by this small polynomial. So here I computed the remainder of the trace polynomial divided by 0 test polynomial. And here the result, it says the remainder is 0. It's because my solution was correct, so this worked. And the way that we are going to test it is that actually the prover will divide it and it get this Q polynomial. And that is the Q polynomial that enable them to prove to other people. If they are lying, then there's no Q polynomial that they can do operation on it. So this is when I divide, I get a polynomial. If not, then you get a fraction which doesn't work for them anymore. Okay. The only problem, so now they can prove that they have a polynomial because you can do operation on it. But if they tell this polynomial to the verifier, first of all, it's big and it's not constant, succinct. It's very big, it's degree 36. So as you see, it has a lot of coefficient. And the second, using that, you can recover R0 and R1, right? So they cannot give this polynomial to them. They just can claim that they have it, and somehow they have to prove that they have it. So I'm going back to the slide, and then I answer question.
Doubt.
Oh, you want to ask question on the okay?
So in this, there's trace polynomial, and then there is 0 test polynomial, right?
Yeah.
And you divided them and got 0. So which part of it is basically like, the prover, I am the prover, you are the verifier.
Yeah.
So the verification is that the outcome comes 0.
The verification is
That when you divide, the outcome comes 0. Is it the verification?
the verification comes to that I have to prove you that I have Q. The division, when I divide these two together, if these two are not divisible, then I get a fraction.
Yeah, that means the verification was
Fraction doesn't have the
successful.
property that you're forcing me to test. and then I will fail.
No, but like the zero that we got, the zero test, and the remainder, basically, if the remainder is zero or there's no remainder, then does that mean that the verification was successful?
But you can't check that because I'm not telling you F and I'm not telling you Q. The only thing you know is the zero test polynomial because there's no secret information to generate the zero test
Yes,
polynomial, right?
right.
So you as a verifier you have that, but I'm not telling you F and I'm not telling you Q. But I'm just telling you that I have Q. Now we have to find a way that you quiz me and then I cannot lie that I have Q. But I'm going to show you.
Okay, so we are halfway there.
We are we should.
Yeah, Marisha. So until now, the work is kind of done on the prover side, and it's trying to kind of work on the proof and not involving first the verifier at the moment, right?
Yeah.
Yeah.
Yeah, but we haven't talked about the verifier
Yeah.
side yet. Yeah. Okay. So that is the problem. We want to do a zero test, but we don't want to tell the polynomial to them. And here, how the polynomial commitment come into the effect. So that's what does the polynomial commitment enable us is that when I tell you I have polynomial fx with some property, and then you tell me give me the value of the polynomial at some random point u. I can give that to you, and I cannot cheat. I have to compute it correctly, and you should be satisfied that I didn't lie. So that is the tool that polynomial commitment allows us. That I can evaluate that you can force me to evaluate a polynomial honestly. Okay. That this evaluation, that when I tell you fu, I don't lie and just generate some random number and give it to you. So what will happen, I'm a prover, I say I found fx because I know R and S. This is the trace polynomial, I found it, and then I commit to it. I don't tell you what is the polynomial, but I commit to it. I give you a number that bound me to that polynomial. And then the verifier, after I commit to it, then the verifier give me a random point and say, if you really commit to that polynomial, tell me what is the value of this polynomial at that point. And because of the commitment, you cannot lie about it. As a result, the value that I get from uv, you are not able to lie about it because you have committed to polynomial before. So how does this work then? So let me go here. So the prover says I have f that satisfies the circuit is 0 at all this point. As a result, because if they don't lie, then there is this, as we saw, they can compute fx and qx such that these values are this relation holds because they got it from the circuit. So then they are going to commit to f and they are going to commit to q. They send the commitment to me, so they cannot cheat after. And then I tell them some random point u and q and tell me what are the value of fq and fu and qu. And then I will put the value of that in this polynomial because this wasn't a secret. And then I verify if the equation holds. And if the equation holds, then it means they actually committed to the real value of q and u. If they lie and they tell me random value, then they cannot evaluate at that polynomial and they are failing. The point is, the evaluation doesn't happen in polynomial. Here you can cheat. It happens on elliptic curve, but I'm not going into the detail of that. This is, okay, there's a question.
Qx also evaluates to 0?
Qx is equal 0? No. What Q?
Qx at the second bullet point or third, yeah. Qx evaluate like fx evaluates to 0.
On 1 to 13, but not Qx. No, because this is a remainder of that. No. Qx is some random other polynomial. If you see it in the Sage, it's there, no? Let me show you on Sage. This is QX.
Okay.
It's some polynomial of degree 23. But they have it because they built a circuit.
Because fx is 0, so multiplying with that also becomes, that remains 0. Okay.
Yeah. But now I'm evaluating as random point u, which is not 1 or 13. None of them. So is it the random value and the polynomial is equal to another value? It's not equal to 0 anymore. Let me go back to this slide.
Yes, Syed.
I'm coming back. Rachel, you're? No, you have it.
Yeah, my question is on on the part whereby the prover commits the polynomials and the factor polynomial to the verifier and their own interaction. But the one thing is, how does the verifier actually has a, I can say, how does a prover prove to the verifier that this polynomial which I'm trying to prove and it actually relates to the circuits and also relates to the factor to the
So I know it's related to circuit because it's 0 at this point.
Okay.
If this relation holds, then this polynomial related to circuit because it's 0 at all point of the circuit.
So the verifier also has the knowledge of that before, right?
The verifier knows that it should be 0 at 1 to 13. Yeah.
Oh, okay. Okay.
The whole point is, but how can they not cheat? Because they know you are going with the u doing that. So they can put some random value v for fu and some random v prime for q, so dissatisfied. Because they can also compute this, but they cannot do that because they have committed to this polynomial. The new value has to come from that polynomial, otherwise the test doesn't pass. So the polynomial, there are different polynomial commitment. Look, so and Stark doesn't use even polynomial commitment, so there is one difference between this and Stark. Planck used KZG in their paper. You don't have to, you can use other method. But KZG is one of the most efficient commitment, that their commitment is very small. So because that FU are just the commitment is just one constant value on a curve. So it's very small. And because you have to send the commitment to the verifier and we want the verifier to not get a lot of data and be succinct, so that's a good choice. It uses elliptic curve cryptography, which I'm not going into it, but it needs a trusted setup. So we talked about the trusted setup before. The trusted setup is some people get together and compute a private key, and then they generate a public key that you need it for proving, for commitment. You need a key to commit. They compute this committing key, and then they have to throw out the private key. If they don't throw out the private key, then they can cheat in the commitment period. Go ahead.
And one question just for clarification. The trusted setup, the keys generated are used for also non-repudiation, right? To prove for even for other people can actually prove the statement using the same keys.
Not really, because you have to throw out the private key. So at the end of this process, there's no private key left. And there's only a public key that nobody knows the private key. So everybody can use it, everybody can prove, right?
Yeah. So I'm saying like the key generated after that, like that public key used to verify the
proof. Yeah.
So it can actually like in a way that not okay. For example, we are one verifier and one prover, right?
Yeah.
But the purpose of storage setup in a way that there can be many verifiers and one prover.
It's true that, but at the stage of trusted setup, there's no verifier and there's no prover.
Yes.
Okay.
Yes, yeah.
But later, yeah, the proof, there could be many verifier. Anybody can verify the proof, and it could be many prover. Anybody who knows the thing can prove, right? But the fact is, to generate it, you need the secret.
Yeah.
There's a question here.
So is this commitment for the circuit, and do we only have to do it once regardless of how many times and who runs the circuit?
No, for every proof you have to commit once. So if you change the RNS, then you have a different commitment. Because the moment you change RNS, the polynomial that you generate change. And then your commitment to the other polynomial is not valid anymore. The polynomial, the trace polynomial is attached to your secret. When you change your secret, then the polynomial change, you have to commit to it again. But if many verifier want to verify it, then that one commitment is enough. They don't need to do it but if you change the secret, you need a new commitment. But the setup is one for all. There is no need to rerun the setup. The key for the commitment is one for all the circuit even. For Planck is like that. Like you can use it for any other circuits.
So can we use like a key that is like generated by someone else? Like for instance, for the Polygon ZK VM, can we use their?
If you trust that they throw out their private key, then yeah, you can.
Okay.
But you need to stick to their setup, right? They use a specific elliptic curve. If you don't like that elliptic curve for some reason, then you cannot. If you need a bigger elliptic curve, then you have to run your own server.
Okay.
So this is called.
Excuse me?
Sorry, go ahead.
Yes, here.
Cool, yeah.
I don't really understand this part of like having a private key and then discarding it. Like, what do we do with it exactly? So, do we sign the operation and then put the
No, we generate. So basically, what you do, you have this private key alpha tau. They call it tau. They like to call it tau. And then you multiply it to the public key. So you get a new public key, right? And then you multiply alpha again with that. So, no, tau, sorry. So you have tau to the power of 2 times the public key. And tau to the power of 3, tau to the power of 4, and you go like tau to the power of 1000. So you have this tau times public key, a lot of them, and you use that for polynomial commitment, but then you throw out tau. If you keep tau, you can cheat and generate polynomial commitments that are
What does it mean exactly to discard it? Like,
deleted SRM. I don't know. You have to burn your computer.
no,
No, search it. For the Zcash, the first ceremony, they filmed themselves that they burned the computer. But okay.
how to make sure that it was actually deleted? That's
Yeah.
That's my
So
question.
that's what happened is that you can do it a multi-party ceremony. So you do your tau, I do my tau, everybody does their tau, and then we add them together. And then if one of us delete the tau, then the final tau is unknown. So if you do it with 1,000 people and one of them is honest, then it's secure. And all the 1,000 people, if all of them are not honest, they all have to collude with each other, put their taus together to recover the key. So that's also another hard thing to go around the world and then to find 10,000 people who contributed to the ceremony. That is why like is good to use the ZK EVM ceremony because it was a hard thing to do. So it's called Power of Tau ceremony because of that, because there are powers of Tau. Tau 1, Tau 2, Tau. Okay. So I'm not going more detail into that, but this is a KZG commitment and it's not very hard. You can easily look at it. It just needs elliptic arithmetic and I'm not going to elliptic arithmetic. So one part remains. That we said a snark is non-interactive, and in this step, I had to send you a U that you didn't know, because if you choose, if the prover knows what U is coming, then he can cheat and choose a polynomial that works for that one U. So they shouldn't see where the U is coming. As a result, this is interactive. So we need to make it non-interactive, and that we use something called Fiat-Shamir heuristic. So what they do, they use the hash function that we love a lot. So they make a commitment and they mandate that the U is a hash of the commitment. So first you make a commitment and then you hash it and you get this random U. And that way you cannot cheat because the moment you change your commitment because that U didn't work for you, then that's the hash changes and then you have to do another thing. So basically, that is by using a hash function, we make it non-interactive. So the verifier will be the hash function, which takes your commitment and hash it and gives a random value back. And that way you have a non-interactive proof. You have a commitment with a hash of it, which is give you U, and then you use U to compute FU and FQ, and then shows that your true proof is correct and everybody can verify it. Okay, so that is there. As I said, in a lot of place, unless you want something very, very efficient, you are not going through the stage that I went into Sage. That if you want just to use vanilla Plonk, there are code written out there that can take your circuit that we wrote in Circom and generate the trace and the other polynomial and then generate the proof for you and let you to verify. So I'm just going to show these few steps that Circom and Snark.js. Snark.js, the tools that generate the proof for you and verify it. How does it work? So you don't need to go through the mathematics of those tables and vectors and Lagrange interpolation. Okay, sorry.
So on the last slide, just like normal understanding for me, we say that making ZK non-interactive and ZK snarks is also non-interactive. First is like with like an example or something, can you tell like what does non-interactive mean and why is it important that we have to make it non-interactive? Because
Why is it non-interactive important? Because otherwise the prover should be always on there and the verifier send the U to them when they want to. Suppose there's a proof that you did your transaction was valid, but then now the validator want to validate your proof. They require to be online at the time so they can send the U to you, so you compute it for them and come back. And that's very impractical because you submit your proof, you want it, the validator without talking to you directly can be able to verify it.
So, and can you please again explain like how we actually make it non-interactive, how we do it?
So the step was like this. I would compute the commitment, I give it to you, but first I have to commit. I cannot do the second step before commitment. I commit, then you come and give me a random U. And then if I'm honest, then I can compute FU and QU based on the commitment I did before. Now what I'm going to do is that, but if you choose U yourself, the prover, then you can cheat. Yeah. So what is going to happen, it says, when you compute the commitment, then you apply a hash function to it. And because the result of hash is unpredictable, you get a random value basically out of it. And then you have to prove you have to compute at that value that the hash function gave you back.
So we compute on the hash.
The random value comes at the hash of
becomes
the
the
commitment.
Hash becomes the U?
Hash of commitment become U, yeah.
Okay.
Yeah, it's like that. And that prevents me from cheating. Okay, so I'm going to generate a trace polynomial using Circom. So I wrote my circuit as you saw, and I'm going to compile it to get the trace polynomial. Okay, so these are all on the GitHub. So, so I have to go. Is it small? I can make it bigger. Maybe I do. Okay, sorry. So I have a folder here called Circuit Example Playground, and I basically tell Circom to compile a circuit. So Circom is going to compile a circuit, but it doesn't still have the secret values. And then from the circuit and the power of tau that I did before, I need to generate the proving key, which is not a secret key, right? It's just a key that I use to commit. But I have to, just to have those keys. So this is the key that I use to do commitment. They are elliptic curve operation as we talked, but they're also, they're public. And then the verifier need another key to verify. So I'm going to generate those two. So I said I want to use Planck. You see, I said I want to use Planck, and I have done the ceremony before for 1,000 power. So it works for up to one polynomial of degree 1,000, and my polynomial is degree 36, so it should work. Oh, there is another thing also here. I think the constraints are 9. The condition are here 9. We did a condition with 13. The reason is they are using something called R1CS is more efficient than Planck because they don't need to consider, they don't make new condition for plus, and I needed for every addition to add new condition. But still, I have more condition, and still the thing was working. So I generated the verifier key and prover key, and now I'm going to generate the witnesses. So I had the secret input. I have to give.
Excuse me,
There's a question. Yes.
sir. What is the difference between non-linear constants and linear constants, and how are they significant?
Yeah, linear constraints are plus, and I think nonlinear are those that has multiplication into them.
Okay, and I mean,
We had a plus, but I think is using a R1CS is not giving a Planck relationship, and R1CS doesn't count for the plus constraint. So any addition in your circuit, you get it for free. Every time you do a multiplication, your degree of polynomial goes up. So I think at the end, the degree of this polynomial is 9. I mean, the degree of polynomial is much more, but the zero test will be a degree 9 polynomial. So, but that polynomial will be smaller than our polynomial. I think because of that the R1CS system, which is not like Planck, it does not need condition for plus. It doesn't add constraint for plus. In Planck, if you have addition and multiplication in the same circuit, it does it with one condition, but if you only have addition, then you add one condition more. But R1CS doesn't do that. So that is my understanding that why they got to a smaller thing than we did.
thank you.
I have also a question.
Okay, sure.
Where did you get the tau from, and are all of the other keys here generated from Circum, or?
I used the Snark.js. I ran the power of tau ceremony with like 2 people before.
Ah, okay.
And but Snark.js has the thing. You say power of tau ceremony and generate. I said to which power you need, and I said power 2 to power of 10, which is 1,000.
And this circuit final.zk and the verification key, are they generated by Circum or?
But it's not JS.
Ah, okay.
Circum doesn't care about the polynomial commitment. So the part of the Circum is basically to generate the trace polynomial, and Snark.js does the polynomial commitment. Here I'm going to tell Circum to generate witness for me. So I give them the 2 witnesses that I have, but as you remember, I added a witness which was another secret input, which was inverse of R-1. So that should be added to this, and all other input that I have to my circuit. So I have to generate those. It generates some JS code that will generate that witnesses for you. So I'm just showing the input file that I gave. So I say R is equal 3 and S equals 7, and I'm going to give that to Circum. To Circum to generate the list of actual final witnesses, because the inverse of it need to be added, and those bits, all of them are secret input. So it'll generate them, and now I can generate the proof using the polynomial commitment with the Snark.js. So I say use Planck, prove the circuit using the key and the witnesses that Circum generated for me, and store the proof in proof.json. And public JSON is a public output. Our circuit doesn't have a public output, so I won't get anything. So if you look at the proof, they are bunch of points and elliptic curves, basically. And this is the curve they are using, BN 128. And then I can run a verifier to verify the proof to say if actually I have the secret R and S, that you multiply them together and you get 21. So a snark use Planck verify using verification key. Public JSON is empty and the proof JSON is what you saw there. And it's return okay. Now another example I wanted to show you was that I use a bad input. So I have this bad input. So I give R as 2 and S is huge, huge number. And if you go to Sage, you see, how can I bring it up? You won't see it anyway. So maybe I come here, no? Sage. But I need that number, so let me copy this number. Right? So if I multiply 2 by this huge number, mod, I call circum prime, I think. Circum prime. I don't know. Let me look at the Sage. Interpolation.sage. Oh, circum underscore P. Sorry. You see? So under the circum prime, this number is 21. And I'm trying to cheat. That I factorize 21 with these two numbers, but they're not actual factor. I use the overflow with the circum prime to get 21. So I have this bad input, which say I have the factorization of 21, which actually is equal to 21. But because I had put, we'll see what you have. So I'm trying now I change my witness. So I'm going to generate a new polynomial, trace polynomial for this witness, right? So I go back into this JS directory that is built for me. And then I say, and instead of doing it for good input, do it for this bad input. What is it called? Bad underscore input. So you see what happened here. I don't know if you see. So it says line 51 of the check factorization, the assertion failed. And this is the assertion that I said S should be smaller than 8, basically. And it failed here, so you cannot generate the polynomial, so you cannot generate the proof. That is the mathematical part of this lecture. There are a few more slides. So we saw how to generate the proof with snark.js, and we saw how to verify it. Okay, so some practical consideration. So as you see, it's a very powerful primitive. Without that, you cannot do private operation on the blockchain. It gives you all this crazy stuff that without this is not possible. We can use it for scaling, like the rollups, and we can use it for privacy, like Zcash. And all this protocol will not be possible without ZK proof, like at least the privacy. Like scaling, you might find a solution. But there are downsides to it. So the prover is very slow, right? All this, when I use a circum for a more complicated circuit, then the size of polynomial become much bigger, and then the prover time goes very slow. And then if you want a faster proof, then you look at your problem. You don't use Planck gate. You use a gate that's, like you see, I wasted some gate here from 9 to 13 because I used the universal gate. Then you have hand optimize it to get a better circuit. And is it's very not. Sorry. So it's not very. It's not like Rust programming language. You see, you cannot have condition. You have to change the conditional of if with something else. Binary operation are slow, modular operation are fast. So they're basically different. So what we did, I just make a summary of all we talked this morning. We talked about the general idea behind the ZK proof. We talked about this application in privacy and scalability. We looked how the mathematics behind it is working and how to generate a sample proof. And we use the normal tools to generate proofs and verify it. That's it for the ZK part of this slide. Question?
Hello, yeah,
Hi.
Vijay. So I just wanted to understand with respect to when we write GK circuit programs, how do we consume it in the blockchain? Like, how do we, since we write the programs in Rust, right, in blockchain space, and if we want to consume JK circuit, how do we like associate that? What is?
Yeah, so usually what you do, you only have the verifier on the blockchain, right?
Mm-hmm.
So that the part that I run snark.js dash verify, like Planck verify, that part should run on the blockchain. And that part is verifying that with the commitment that zero test passed, for example, right?
So this verifier is put it on the blockchain to verify? Or?
Yeah, it looked like a smart contract, right? Or
Okay.
like in Zcash, it's just logic on the blockchain. What it takes the proof that came, somebody submit a proof, which is just a bunch of bytes, which are representing this point and elliptic curve, and then they run some elliptic curve operation on them, and if the equality ended up being there, then accept. It's very similar to when you do a transaction. No, you have a signature. The code on the blockchain will check if the signature actually satisfies. If satisfied, then transfer the money, right? So here is also just the verifier is some electric curve operation, which is the KZG. So if you look at this, that is only the operation you need to put it on the blockchain to verify that's the commitment is and the value after that is valid.
So are we going to see any example in coming classes to figure out like how we do this kind of interactions with the GK circuit and after deploying and interacting with the smart contracts or maybe the chain?
I haven't said anything here. I can.
Because it's very much like vague in the mind, so just to.
Still, it wasn't enough demystifying. I have written a blog post. I don't know if you want to look at it. I don't know if it's the best thing also in the world, but so we use a sample ZK rollup for the validator's key. So what we do is that I talked about BLS signature yesterday. So what we do, we make a proof. So instead of aggregating the key, we make a proof. So aggregating the key is not easy because you need all the public keys together. And instead of giving the public key to the verifier, we are going to aggregate all these keys ourselves, and we just prove that we didn't cheat while aggregating. It's not the easiest ZK problem, but I tried to write a simple blog post on it. I'm just showing you where is it. It's called APK proof with hand and sage. It goes through this problem, and step by step it says what to do. So the problem is obvious. We have n validator, they sign something and we wanted to aggregate them. But then at some point, we have to do the ZK part. Then it generates the snark. It talks about the snark, which you're not very interested in. The snark is much more complicated than what we saw here. But the end part is there. So it does this ZK, the KZG that I didn't talk about. It finds these elliptic curves. And at the end, it does somehow it goes proof and verify. This part you don't need. The only part you need is verify, right? That is done on the chain. So I'm going down to see the verification. So this is the tau here that is basically going to happen. It happened on elliptic curve. Maybe it's not the simplest example, but the good thing about it is every every step of it one by one has been, the math has been done, is a more simple one. We could, if you want, we could write the verifier that we did for this. Today, maybe it's too much here, I'm sorry. But if somebody wants another simple example, this one is there. Is not the simplest example in the world. We can do it as activity. Maybe, you know, if you finish your assignment and then you're bored, we can sit together. We have to do the power of tau. So that is a cool thing to do together. Because I used the 89 because I knew I have a good curve. Then we can generate the curve and then basically write the Rust code that verify the proof together.
Thank you.
You're welcome.
I have a question. I'm Gunjan.
Where are you? I don't
This
see.
side.
Oh, here. Sure.
Thank you. So we have a statement which we prove, and that is verified. So verifying the statement is one thing. Once it is verified, the statement is going to be used. So chances of replay attacks are here as well. So
Considering what?
replay attack. So
Replay attack. Yeah.
So
It's a
suppose
problem.
somebody is only checking if the proof is correct, then they can send the proof of anything and get the advantage of other things.
Yeah, they get money more and more and more from your account, right?
So what are the recommendations to avoid such replay attacks?
So the one that I know is the nullifier. So what will happen is that every transaction, for example, in Zcash, has a nullifier attached to it. And then I want to send the money to you. I submit this zero knowledge transaction. I'm a prover, and I say I had the money. I transfer it to this account. At the same time, I submit this nullifier to that transaction, which is completely attached to it. And then they get that nullifier and they store it in the database, which you can put in a Merkle tree, for example. And then the second person that submitted, when the transaction is submitted, you look into the Merkle tree before the blockchain to accept the transaction. Not only the power of the thing should work, like the ZK commitment should work, they also check the Merkle tree to see the nullifier is not there. If the nullifier is there, then they won't accept. Even that the ZK proof passed, because somebody has already used it, then they won't accept it.
Yeah, that's cool.
And the only person that can submit the nullifier to be accepted is the person who has the key. So somebody else cannot randomly come and cancel your transaction. When you make a transaction as your thing, you also submit a nullifier with it, and then they store it there and they won't accept it anymore.
And if the context requires putting timestamps in the statement, is it a good idea?
Maybe, but it's not a bulletproof, no? They can submit twice at the same time. Some nodes will send it to somebody else, and yeah. I don't know. I don't think timestamp is a reliable solution to that. Yeah.
Thank you.
So little bit going to the ground zero to actually like just testify that my understanding after this is correct or not. So what we had initially is that R into S is equals to N was a truth or a secret. That we know R and S that equals N, which people know, and N is something that everyone
Everybody know, and it was actually a constant. It was 21,
So then what we did is then we created R and S in form of polynomials so that we can compute on.
No, then I added more condition. I added more condition, right?
Yeah.
I say it's not enough for me to tell me RNS is equal to 21. It's not an interesting problem.
Yeah.
I also wanted to not to be 1, and I wanted to not overflow.
Yeah, so you added these 3 conditions, and then you represented R and S.
I represented the polynomial, the conditions as polynomials.
Conditions as polynomials.
Yeah.
Okay, and then basically, I will compute my R and S values on these polynomials.
On this condition, yeah, and put them in that table.
Right.
But I use that table to write the polynomial in a specific form, so
yes,
I can put them in one column and then do the fast computation.
And then I also do use this RNS to another polynomial.
So at this level, then we didn't have any polynomial anymore because I put the RNS in those condition polynomials, and then it became constant, right?
Yeah, we got a return.
So we
yeah.
only had the table of constant. And
Table
then I
of
took that
constants.
table of constant and turned it into one big polynomial.
Yeah, the
Using
Q
polynomial
polynomial.
interpolation has nothing, I mean, it has something to do with those polynomials, but are not the same as the
And
condition.
the U operation was done on that new polynomial, right?
Then all the operation is happening on that polynomial.
Yeah. My question in this whole was, where did we skip the conditions that we actually had, like the real world conditions, for example. Here, what we just proved is that, hey, this is my private key. What I did through this process was, I generated, in this factorization example, I generated a proof that I hold a secret, that is the secret of multiplication of my prime numbers, which is my private key technically.
Yeah.
So where did the conditions and attestations or proofs for the things like maybe, this transaction is signed by this, or my balance is over this, how did we prove this, or how did we create proofs for
How
that?
are we going to prove that?
Yeah, because
That is
in
what
this,
you're
it's
telling
just
me.
for the private key. I could have just signed it and then you could know. We
Yeah.
didn't need
But
ZK proof for
look,
just for
when
this
you
case.
sign, what do? You do operation elliptic curve.
Yes.
And that is an algebraic operation. You multiply something divided by something else,
Yeah.
and you get a result.
Right. So
And you can write that an n times r times s was algebraic operation.
technically, but the end goal, I'm thinking of the end goal is that with this factorization example is what we got is that you hold a multiplication to prime numbers.
Yeah, so I
that
have
is your
this private key that when I multiply it
and
to
you proved it to me that you hold it, right?
Yeah. So what I'm doing, I prove that I hold the private key using elliptic curve operation,
Yeah.
and I'm transferring this money from here to here.
And this was a ZK proof. But
Yeah.
Where does these conditions come, or these proofs, how you verify to me that you have this much balance on chain, or you have, for this private key, you have this much data? Where does that equations, or how that would work? Because here is just that you prove me that you have a private key, right? With the ZK proof, you just prove me
No,
that-
but I also show you that had a valid UTXO. So that is how I have the balance. I can put a condition for that too.
So you have to add the condition at the level where you have added
have the
initial three
balance.
conditions
Yeah.
or on RNS.
So how does UTXO work? It's like a valid transaction that's signed, and it says the money will go to this account.
Yes.
So I can put that the whole thing that there's a signature on this for this amount inside that.
So you have to. My question was, where do you add these conditions? Which point you add?
Oh, I see. So I had few condition here. R times s is equal n. I can add another condition.
Before you generated the Q polynomial.
Yeah, the table become like 1 million line.
Yeah. Before the table, you add these conditions, right?
I add them to the table. Each of these condition will add one line to the table. Yeah, before that I will write them and then I make a table of them.
Right. Where we added these conditions, like it can't be one.
Yeah, exactly. And the
okay.
other one is the UTXO is valid and the signature is valid. All of them become many line on the table. Yeah.
Got it. Thanks.
I guess we are going to stop here. And